This tutorial discusses the first law of thermodynamics. The first law of thermodynamics is the law of conservation of energy. When energy is exchanged between objects or transformed into another form, all the energy is still there. That's really important, meaning that what's there at the beginning will be there at the end. It just seems different. The total amount of energy in the universe before the change has to be equal to the total amount of energy after the change. You can, therefore, never design a system that will continue to produce energy without some source of energy to begin with. So let's talk about the energy flow and the conservation of energy. Conservation of energy requires that the total energy of the energy change in the system and the surroundings must be zero. Remember the definition of system and surroundings. The system is what's being observed, while the surroundings is everything else in the universe. So energy can come out and go into the system, but the net total has to be zero. So the energy of the universe, the energy of everything, has to be zero, which is the systems and the surroundings added together. This triangle here that you keep seeing, you're going to see that over and over and over again. That means change. It means the final minus the initial. So as the energy gets lower of the system, the energy is going to go up in the surroundings because they must be transferred from the system to the surroundings. The internal energy is the total amount of kinetic and potential energy the system possesses. The change of the internal energy of a system depends only on the amount of energy in the system at the beginning and the end. So it doesn't matter how it got there or what happens during it. All that matters is the final and the initial. This is called a state function. It's a mathematical function whose result depends only on the initial and final conditions, not on the process used. So it's the final minus the initial, or the delta E of a reaction is the products minus the reactants. Give me another example of a state function. Here's a mountain. No matter what, the mountain is going to be 10 feet high. It doesn't matter if you take path B, which is only 5 miles, or the easier path of A, which goes back and forth of 12 miles. The final result is going to be 10,000 feet, regardless of how you get there. The mountain is a state function. It depends only on the distance from the base to the peak, not how you arrive there. So let's talk about energy diagrams. Energy diagrams are a graphical way of showing the direction of the energy flow during the process. So the internal energy, the final over the initial, or this one has the initial over the final, meaning that the final is lower in energy than the initial is. If the final condition has a larger amount of internal energy than the initial condition, the change in the internal energy will be positive. So we're talking about the internal energy of the system. So if the energy goes up in the system itself, it had to come somewhere, so it's coming from the surroundings. However, if delta E is negative, the final condition has a smaller amount of energy than the initial condition, meaning that the system gave off energy in the process. So let's talk about this energy flow. When energy flows out of the system into the surroundings, the energy flows, the system itself is a negative because it's flowing out. It's giving off energy. So the energy is less when it's done. When energy flows into the surroundings, then the surroundings is going to be a positive because the energy is given to the surroundings from the system. So the energy in the outside actually increased. So the system is the energy is going from the system to the surroundings. So the system is losing energy while the surroundings is gaining energy, which is why that's positive. Notice that the delta E is going to be the same with just this change. There's a negative delta E for the system because it's flowing out, and a positive for the surroundings because it's flowing in. How about the reverse? When energy flows into the system, it must come from the surroundings. When the energy flow in the system is positive, that means that the energy inside went up. When the energy flows out of the surroundings and into the system, the surroundings is negative. So this is exactly the opposite. The surroundings lost energy, which is why it's negative, to the system, which is why that's positive. Once again, delta E, same magnitude, but the surroundings is negative because it's lost energy. The total amount of internal energy in 1 mole of carbon and 1 mole of oxygen is greater than the internal energy of 1 mole of carbon dioxide. This is why when you burn something, it gives off energy in the process. This is at the same temperature and the same pressure. And the reaction carbon plus oxygen yields CO2, there is a net release of energy into the surroundings, which is why you feel the heat. This should be a capital E. In the reaction of CO2 yields carbon plus oxygen, it's the reverse. There will be an absorption of energy from the surroundings into the reaction. So the surroundings is losing energy, which is why it's negative. So let's talk about energy exchange. Energy is exchanged between the system and the surroundings through heat and work. Q is heat, which is thermal energy, while W is the work energy. Q and W are not state functions. Their values do depend on the process that it takes. So here is the overall. The change of energy is Q plus W, the work and the heat added together. So the heat is positive when the system gains heat energy, and it's negative when it releases heat energy. Work is positive when it gains energy from work, and negative when it releases energy by doing work. Finally, delta E is positive when overall the system gains internal energy. If it loses internal energy, it's going to be negative. Energy is exchanged between the system and surroundings through either heat exchange or work being done. So it's going back and forth. So let's talk about that a little bit more in physics terms and something you can relate it to. On a smooth table, most of the kinetic energy is transferred from the first ball to the second ball, with a small amount of energy that's lost from friction. So if you originally hit the ball at 5 joules, some of the heat is lost through the friction, but you still have most of it left over. The final amount is -5. If you're working on a rough table, like a really old table, you still hit it with the same amount of force. However, much more of the heat is being lost during the friction. So it hits it at 2 joules. So you're losing it by 2 joules from transferring. You lose it 3 joules from the heat, from the friction. It's still going to come out to -5. It's still going to have the same final amount. In the previous billiard ball example, the delta E on the white ball is the same for both cases, but Q and W are not. On the rougher table, the heat lost Q is greater. Q is a more negative number. There is more friction involved. But on the rougher table, less kinetic energy is transferred to the purple ball, so the work done by the white ball, W, is less. W is a less negative number. The delta E is a state function that depends only on the velocity of the white ball before and after the collision. In both cases, it started with 5 kilojoules and ended with 0 because it stopped. The Q plus W is the same for both tables, even though the values of Q and W are different. And that gives you an explanation of how the system and surroundings transfer heat and energy.